In the last video on this channel, I went over a problem from Pythagoras Quest, which is a math competition for middle schoolers in Sweden. And in the last one, I was sort of ambivalent about what I felt about the problem, but this time it's just sort of a fun problem that I saw and that I had, kind of a good time solving. It wasn't really a big deal in terms of making a point or anything. I just wanted to go over this problem as well because, I found it enjoyable to solve. And the task is to find the relationship between the radius of the big green circle and the radius of the small orange circle in the image. As with all problems from Pythagoras Quest, you don't need advanced theoretical knowledge to solve this problem, but it does require that you know all the basics of Euclidean geometry. And just because you don't need advanced theory to solve the problem does not mean that the problem is easy to solve. Now, if you want to solve this problem on your own, feel free to pause the video and then come back when you're ready for the solution. Let's talk about how we actually go about solving this problem. And the solution strategy can be sort of divided into two separate phases. And both of these phases require that in this image that we have, we assume that what you see is what you get. Basically, if a triangle like this large one looks like it's right angled, then it is right angled. If this figure here seems like it is a square, then it is a square. If this circle here, the blue one, seems to lie tangent to all of these different sides, then it does lie tangent to the different sides. And if a bunch of circles, like the blue ones, seem to be equally large, then they are equally large. Same with these orange circles, and same with these points of tangency between orange and blue circles. But when we have all of this information, basically what we can do to solve the problem is to use the square over here to find the relationship between the size of this orange circle and the blue circle. And then we use these two triangles that are tangent to the green and the blue circle respectively to figure out the relationship between the green circle and the blue circle. And now all of this works because of similarity of this triangle here to the left and this smaller triangle above the square. So let us now zoom in a bit on this square region and see how we can complete the first phase of the problem, which is to find the ratio between the radius of the small orange circle and the slightly larger blue circle. Zooming in on the square shape in the image, let us mark out some points of interest. First, we mark the center of the upper blue circle. Then we mark the center of the leftmost orange circle. And finally, we mark the point of tangency between the two blue circles. Next, we add in lines connecting all of these points. Now, with the triangle that we have on the screen right now, basically what you see is what you get. For instance, this point of tangency between the orange and the blue circle indeed does lie on this distance between the two center points of the circles. Moreover, the angle between these two lines is indeed 90 degrees, making this triangle a right-angled triangle. Let's see how we can use this to set up an important equation for later. Now, I've added some notation to make it easier to see what the equation we're going to set up is supposed to be. But one thing I want to note is why I've set the length of the blue circle to be equal to 1. And this has to do with the fact that it really doesn't matter what the absolute length of anything in the image is. All that matters is what the relationship between lengths in the image are. So I can scale up or scale down the image without changing these ratios at all. So I can just scale the image so that this radius is equal to 1 unit of length, no matter which unit I'm measuring in. And I'm doing this to simplify some of the algebraic calculations later on. Using the notation in the image, we get the following using the Pythagorean theorem. So we get that r plus 1, which is the length of the hypotenuse in the image, squared is equal to 1 squared plus this r plus x squared. So we get plus r plus x squared. And now what happens when we expand both of these squared terms? So we get r squared plus 2r plus 1 is equal to 1 plus r squared plus 2 times r times x plus x squared. And now we can simplify a bit. We see that both r squared terms cancel, and we see that the terms 1 cancel as well. So we get that 2r is equal to 2r times x plus x squared. And now I will factor the right-hand side of the expression because I see that I have a common factor x in both terms. So then I get that 2r is equal to x times 2r plus x. At first glance, it may not seem like this relationship will yield us anything of value, but looks can be deceiving because we haven't really extracted all the information we can extract from our image of the square. Now, I've added some distances in this image here, like this distance from the center of the blue circle all the way up to the upper edge of the square. And what I end up with is a distance from the point of tangency between the blue circles and all the way to the upper edge of the square, which is equal to 1 plus 1, which is equal to 2. Likewise, I've extended the line segment between the center point of the orange circle and the point of tangency between the two blue circles all the way to the leftmost edge of the square, adding a distance of r, which means that from this I see that this total distance is now 2r plus x. And from the image, it should be visually apparent as well that both of these two distances are the same. And this simply means that 2r plus x equals 2, which will be very useful for us moving forward. Now, the relationship that we just discovered between r and x can be used to simplify this factor 2r plus x and just replace it with 2. And we end up with the equation that 2r is equal to 2x. Now, canceling out 2's on both sides, we end up with r is equal to x. And this identity can be used to simplify any of these lines in this equation over here. And I will actually use it on this final line to get the following, that 2r is actually just equal to r times 2r plus itself. And now I can cancel out the r's on both sides, and I end up with 2 is equal to 2r plus r, which is equal to 3r. And now I divide by 3 on both sides, and I get that r is actually equal to 2/3. And this marks the end of the first phase of the solution to this problem. Let us now move over to phase 2. Phase 2 of the solution is all about finding the ratio of the radius of the blue circle and the radius of the green circle. And once again, we set the radius of the blue circle to 1 just to make some computations later on a bit simpler to perform. In order to find the ratio that we're after, we need to use similarities because there are many of them in this image. For instance, if we look at this leftmost triangle containing the green circle, this triangle here is actually similar to the upper triangle containing the blue circle. And this means that all corresponding sides in the upper and the leftmost triangle have the same ratio. So for instance, if you take this length divided by this length, it will be the same as taking this length divided by this length, or this taking this length divided by this length, or taking this radius divided by this green radius over here. And this is the key realization that we have to make. We just need to find ratios between two of the sides in these triangles, and we are basically golden. More concretely, I will try to compute the relationship between this height of the upper triangle and this height of the leftmost triangle, which I know a lot about already. I know it's the side of the square which means that I already know how many units of length it is, because I have these two blue circles stacked on top of one another, so I know this distance is just 2 times the diameter, which means it is 4 units of length, which is also then this side of the same square. So I already have a lot of information, so all I need is to somehow calculate this height, and I will basically be golden, because this height divided by this height is the same as this radius divided by this radius, and that's all I need to solve this problem. For the sake of clarity, I've decided to focus on the upper triangle from the original image, because as long as I can compute this height marked in brown, I can easily compute the ratio that I'm after, because I know that that ratio will have to do with this side length of the triangle, which is just the side length of the square, which I know already to be equal to 4. Now, I will solve this problem using coordinate geometry, and I will introduce the coordinates of 4 very specific points in order to do this. I'd like to explain why I've chosen the points and the coordinates the way I've done in the image below. So first off, I've chosen this leftmost lower corner of this triangle to be my point of origin. And we shall see that this is a very good choice given what I'm about to calculate. Also, given this point of origin, I can easily find the coordinates of the points M and Q, where Q is the point of tangency between the blue circle and this lower side of the triangle. And since this is the lower side of the triangle, we have the y coordinate is of course equal to 0. And we also know that this distance from Q to this height marked in brown must be the same as the distance from M to the height marked in brown. And we already know that this is equal to 1 because it's just the radius of the circle. So this distance here must be equal to 1. And then in order to have that this total length is equal to 4, we need that the distance from O to Q is equal to 3, giving us the coordinates of the point Q to be the x-coordinate 3 and the y-coordinate 0. And from this, it's very easy to find the coordinates of this point M, because M is just one step in the y direction above Q. So we get the same x-coordinate, which is 3, and the y-coordinate equal to 1 instead of 0. The one point that I've marked out where I don't actually know the coordinates in advance is this point P, which is the point of tangency between the hypotenuse of my triangle and the circle. And I've marked this with coordinates x and y. Now, if I can find the coordinates x and y, I can easily from this deduce the ratio between this height of the triangle and the base length of the triangle. So now let's figure out how I can, given the information from the points I've already added in the figure, get the coordinates for x and y. First, I will claim that the distance between the points P and M in this coordinate system is equal to 1. And this should really come as no surprise. We have that this is the point of tangency of the circle, we have that M is the center point of the circle, so obviously this distance is just the radius of the circle, which is equal to 1. My next claim will be about the distance from P to the origin, and I will claim that this distance is actually equal to 3. This statement is far less obvious than the statement that the distance between P and M is equal to 1, and ultimately it has to do with the fact that this hypotenuse in the image is a line of tangency, and it goes through the same point as this line of tangency. And since we know that this distance between O and Q is 3, we also know that this distance has to be equal that distance, because they are both tangent lines that pass through the same point. This is not an obvious statement. You have to understand how to prove it, but it is indeed true, and I will not go into the details as of why it's true right now. However, using these distances, together with the fact that we can express distances using coordinate geometry, we can get some relationships that x and y must satisfy. First off, we get that this distance squared must be the difference in x coordinates between the points and the difference in y coordinates of these points. And we take the sum of the squares of these differences. So we get that, first we get that x minus 3 squared plus y minus 1 squared must be equal to 1 squared. So this is what we get from the distance between P and M. Now, from the distance from the origin to P, we simply get that x squared plus y squared is this distance squared. So we get that this is equal to 9. Let's expand this line right here. We get that the first term becomes x squared minus 6x plus 3 squared, which is equal to 9. And then the second term becomes y squared minus 2y plus 1. And this is equal to 1. And now these ones cancel out, and we have that x squared plus y squared is equal to 9. So this expression here simplifies to minus 6x plus 9, so plus 18, minus 2y is equal to 0. Or rather, that 6x plus 2y, if we move both of these over to the other side, is equal to 18. We can also simplify this one bit further, and we get that 3x plus y is equal to 9. At first glance, it may not seem like we can do very much with this, but we can actually use this relationship between x and y in this equation, that x squared plus y squared is equal to 9, to gain even more information about these two numbers. Because here we can actually write that y is equal to 9 minus 3x, which means that we can use this and get substitution in this equation right here. I'm going to clean this up a bit so that we get a clearer sense of what we're actually doing. Let us now try to solve this equation by substituting for y this expression 9 minus 3x. Then we get that x squared plus 9 minus 3x all squared is equal to 9. And let us now expand this expression. So we get x squared plus 81 minus 9 times 3 times 2, which is 27 times 2, which is equal to 52, minus 52x, and then plus 9x squared is equal to 9. And now we can simplify a bit. We can move this 9 over to this side, and we get that 10x squared plus 72 minus 52x is equal to 0. And now I will leave it as an exercise to solve this equation fully. If you calculate correctly, you get that you have two solutions. First, we have x1 equal to 3, which leads us to the first y1 equaling 0, corresponding to the point Q. But then we have also the other solution, x2 equals to 2.4. And this leads to y2 being equal to 9 minus 3 times 2.4, and that is equal to 1.8. So that means that this point here is actually equal to the point 2.4, comma 1.8. And those are the x and y coordinates. At this point, there isn't really that much left to do besides noting that what we're after, which is the ratio between this base length and this height, is the same as the ratio between the x and y coordinates of the point P. This has to do with the following construction. If we add this line perpendicular to the base, we will construct a triangle which is smaller than this larger one and is similar to it. So this triangle with base equal to 2.4 and height equal to 1.8 will have all the same proportions as this larger triangle. So we know that this ratio between this base length and this height will also be 2.4 divided by 1.8. And we can actually calculate this ratio pretty simply. So this ratio that we're after is equal to 2.4 divided by 1.8. And we can multiply both of these by 10 to get 24 divided by 18. And we can simplify this a bit by factoring both the numerator and denominator. So we get 6 times 4 divided by 6 times 3. Cancel out the 6's and we're left with 4 divided by 3. And this is then the ratio between this base length and this height that we were after originally. Let us now step back a bit to summarize what we have figured out so far. So, we just computed the ratio between this base length, which is 4, by this height, and computed it to be 4 by 3, meaning that this height is actually equal to 3 units. But this means that the ratio of this height divided by this height is also 4 by 3, because we know that this side length is also equal to 4 because it's also one of the sides of this square. So we get that the ratio of corresponding sides in these two similar shapes is always going to be 4 by 3 when comparing the larger to the smaller one. And this includes the ratio of these radii. So we get that the radius of the green circle compared to the radius of the blue circle will also have this same relationship, that it is 4 divided by 3 times the radius of the small blue circle. So we get that this radius r is equal to 4/3. We also have that this small radius is equal to 2/3. So let us now summarize this and compute the ratio between the large green radius and the smaller orange radius. We get that large r divided by small r becomes 4/3 divided by 2/3. Now the thirds of course cancel and we're left with 4 divided by 2, which is just equal to 2. So the large r is 2 times as large as this small r of the orange circle. And that is the full solution to this problem. At this point, if you're still here, all I can say is thank you for watching the video, and I really hope that you got something out of watching this solution. If there were any steps or explanations that you found unclear, feel free to comment below and I will read them and address them as soon as possible. But I don't really have much more in lines of insight to give, so for now, have a nice rest of the day wherever and whenever you are. Goodbye.